All right. So we're going to dive right into de novo pathway design. And one thing that I wanted to clarify from kind of the outset of this lecture is what we mean by de novo in this case. It can be a little confusing because in metabolic engineering, de novo can have two meanings, and sometimes it can be used to mean both. Sometimes it can be one or the other. And these are related meanings, so it's not that big of a deal, but it's useful to understand that these options are there. So de novo is a Latin phrase meaning of new, from the beginning. And what you can see is that there's this idea of de novo synthesis or biosynthesis. And so de novo synthesis is actually also a term that's used in chemistry. And both of these mean that you're making a complex molecule starting from a simple molecule like sugar or some other input. This is like the idea of total synthesis in chemistry. But there's also this competing meaning for de novo, a de novo pathway or de novo enzymatic steps. And what that's referring to is more that the route is what's new. Rather than starting from a simple molecule, a de novo pathway design is a route to a metabolic product that's often unnatural and reported for the first time. Because if it was natural and if somebody had already done it in that organism, depending on again, maybe some aspects of your definition, it might no longer be considered a truly new pathway design. And so our focus in this lecture will be on metabolic products that are not already present within your target organism. We're going to be focusing more on this idea of de novo pathways. And the first thing to kind of say about that is that de novo pathway design might not be necessary. So whether it's for your group projects or other examples maybe in the homework that have come up, you know that you don't always need a new pathway to get to some kind of metabolic product when in fact you can do a couple of other things. So from this review from 2008, and we'll see a few different illustrations of this, so I won't dwell on this point too much here, but you can see that there are other ways to get to metabolic products. One of the first things to think about is if your organism already has your metabolic product, then it already has the pathway. Then you would go back to or more conventional up and down regulations, knockouts, etc. But let's say, as I said, the focus would be your organism doesn't have that metabolic pathway. So then the question is, are you going to just take a pathway from a different organism and just sort of plop it in through heterologous expression, maybe harbored on some kind of plasmid, and then you have a pathway that your organism gets to, and then you're just recapitulating what another organism might do in order to get to product P here. So that's combinations of existing pathways. You could also tweak or branch out from an existing pathway. This implies maybe you're just adding one enzyme or two, but you're mostly just following a pathway that is either already in your organism or from a different one. And this is all meant to be in contrast to the idea with de novo pathway design that you have this product in mind, and especially if it's not naturally occurring, you don't have some other organism that makes that you're just going to move all the genes from that pathway and put them in your organism. What you're going to go through instead is some kind of exercise where you piece together, often from different organisms, different enzymatic steps that get you to that final product, potentially, thus creating a new pathway that's really not seen in nature. And so that That's what we're trying to get to. So to try to frame this a little bit better, I mentioned something that doesn't exist in nature. And I thought that this image, though it can be confusing if you just look at it without explanation, can help guide what I mean here in terms of what metabolic engineers could engineer organisms to make. So if we imagine this kind of bacteria here, the center, maybe it's E. coli, taking a renewable source of biomass and then potentially converting it to different categories of products, you can have this different classification based on what's available in your host or not, and what's available in nature or not. So if it's something like, take succinic acid, naturally occurring metabolite in the TCA cycle that we've talked about before. It's in just about every organism, at least ones that have a functional TCA cycle. And so then if you want to make more of it, you perform certain strategies, and you don't necessarily have to do any kind of de novo pathway design. That's because this is both a naturally occurring compound and it's inherent to your organism. So some of the other examples that I mentioned related to the previous slide, where this is something that's natural, but it's in a different organism, you could potentially move a pre-existing pathway directly from that organism, or there's still opportunity for de novo pathway design here, because it might be that that organism makes that product in a really inefficient way, and you're going to come up with a new route. And we will talk about an example like that, something that's natural and non-inherent to yeast or E. coli is vanillin or vanillin, which we talked about earlier, but not in this context. The pathway that was engineered for vanillin is not the same pathway that the vanilla bean plant would, the vanilla pod, I suppose, yeah, the vanilla plant, it's not the same pathway that the vanilla plant uses. So you can also have non-natural metabolites that are made via metabolic engineering. And in those cases, it's not going to be inherent, and there's more opportunities for de novo pathway design, sort of almost by definition in these cases.